Okay, good morning everyone. Welcome to the first video about intermediate quantitative research methods. We're going to use my course book, Introduction to Quantitative Research Methods. This is a book that is licensed under the Creative Commons license, as you will see on the first page. If you don't know what this means is you're welcome to use this book, to share it, but you need to give me credit for any materials that you use, which is about attribution. You may not sell it, which is what the non-commercial part means. And share alike means you should share anything you get from this with other people on the same basis. And as you'll see at the bottom, this was last updated on March the 3rd. Now, I'm assuming in this course that you have already got done a fundamental research methods course. So if you haven't, if you're not clear about Occam's law and research methods, please look at chapter 1. If you're not clear about different types of variable, that's also included in chapter 1. Chapter 2 covers association and causation. Chapter 3 covers research design, including probability samples. Chapter 4 is a very brief summary of qualitative research. Chapter 5 is about measuring instruments and how to evaluate them, including reliability, validity, and precision. Chapter 6 is the 3 basic laws of probability. Chapter 7 is about statistical computing. Chapter 8 is about summarizing data using graphics or numbers. And then chapter 9 is the basics of estimation and hypothesis testing. So I encourage you to skim over these and check that indeed you do know all these things quite well. And we're going to start from chapter 10, which is about relationships between pairs of variables. So let's go to page 117. Let me just quickly scroll down to there. So page 117 is, okay, let me go back to full screen so we can see it as clearly as possible. So we're going to, the learning objective for this chapter is how to understand statistical tools for relationships. So if we don't know what sort of relationship there is between a pair of variables, the best starting point is usually a graphical display or a table. For variables that are categorical, we often use a table of counts, but as we will see, there is a graphical option called a mosaic plot. If they are both interval or ratio scale, we use a graphical display called a scatter plot. So we're going to look at 2 examples. The first example is with 2 nominal scale variables. So if you don't remember, nominal scale means they're categorical but with no ordering of the categories. And then we're going to look at another example with 2 interval scale variables, which means that differences in values are meaningful. So the example with 2 nominal scale variables is a very simple opinion poll. It's an opinion poll of men, and it looks about their preferred car type and it looks at their marital status. So the key question is to understand whether there is association between your marital status and your preferred car type. So let's have a look at what we see. So on the left here, we can see a mosaic plot. So a mosaic plot gives us a nice graphical representation of what's going on, where the horizontal axis is marital status, married or single, and the vertical axis is the type of car, family car, sporty car, or work type car. So when you look at the graphic, it's very clear that the proportion of single and married who choose a work car is very similar, but we can see there is a fairly large difference apparently between the proportion of single and married men who choose a family car versus a sporty car. So that graphic shows us very clearly what the apparent difference is. What it doesn't tell us is that difference big enough to be due to chance or not due to chance? So for that we need to use a statistical test. And what we have on the right hand side up above is a table. So in that table you can see we have first of all the count, in other words how many of these men chose a particular combination. Then we have the percentage of the total. The total is 303 respondents. Then we have the column percentage and the row percentage. So how would we be able to identify whether there's association? So for this we use Pearson's chi-squared goodness of fit test. And this uses the idea of one of the probability laws. So one of the probability laws says if we have independent variables, then the probabilities multiply. In other words, if there is truly no association between marital status and type of car, then the probability of somebody being married and choosing a family car should be the probability of being married times the probability of choosing a family car. So if we look at that particular combination, you can see that around 2/3 of our respondents were married, 64.69%, and about half of our respondents chose a family car, 51.16%. So 2/3 times a half, and we have 303 respondents. That's about 300. So 2/3 of 300 is about 200, times half is about 100. So we would expect if there was no association between marital status and type of car, that we would have about 100 family car choosing married men. In fact, we have 119. So in the Pearson's test, we compare the counts we observe, which is 119, with the count we expect. So we have 119 minus 100 all squared, which is about 400. We scale that by the expected count, which is about 120. So that's close to 4. We then need to repeat that calculation for all 6 cells in a table. If we add it up, you will see that the Pearson's chi-squared statistic is 26.963. And if we check that against a chi-square distribution, and it turns out it's chi-squared with 2 degrees of freedom, then it turns out that's very strongly significant, statistically significant. So it's almost impossible for us to get data like this by chance if there is indeed no association between marital status and car type. Now, why is it 2 degrees of freedom? There's 6 cells in the table, so that does seem a little bit odd, but you need to remember that we have used the information in the row totals and the information in the column totals. So if I work out the number who are family and married, I can find also the number who are single and family by subtraction from the family cars. Once I have the married family and married sporty, I can work out the married work car by subtraction from the married row total. So in other words, once I know 2 of the numbers in this table, I can work out the other 4 by using the row and column totals. So that's why there's only 2 degrees of freedom. So in other words, the statistical test tells us, yes, there is some association between marital status and family car type. We can see what that is from the graphic. We can see it's clearly that married men are more likely to choose a family car and single men are more likely to choose a sporty car, but the proportions who choose work cars are similar. So that's not really important. It's really that choice between a sporty car and a family car. Now we need to be very careful because this just tells us there is an association. It doesn't tell us what is cause and what is effect. So in the earlier chapter we talked about association, So what might be the issue here? Well, for example, the most likely thing we would expect is that if I'm married, I'm more likely to choose a family car because I need it as part of my marital status. But I don't know. It could be that indeed it works the other way around. It could be that because I drive around in a sporty car, no woman wants to marry me because she realizes I'm not suitable to be a married man. So it could be that my choice of car is determining my marital status. Or it could be that what's really explaining all of this is personality type. In other words, some men have a personality type that means they both prefer to be single and they prefer a sporty car. Other men have a personality type which means they both prefer to be married and prefer to have a family car. So we cannot tell from this table or data set alone what is cause and what is effect, but we can be quite clear there is an association and that what we see in this table cannot be due to chance. Okay, so the next page in the course book explains in words what I have just explained to you. Sorry, this is in writing what I've just said to you orally about how we have been able to do this test, how we got the degrees of freedom. Now, one more point I want to make very clear here. You'll see it has a note saying there are more powerful methods if the variables are not both nominal scale, such as Spearman's rank correlation if both are ordinal scale, and Kruskal-Wallis test if one is ordinal scale and one is nominal scale. So remember, ordinal scale means there is some ordering of the categories. So if there was some ordering of our categories, then there are better methods than simply using Pearson's chi-squared goodness of fit. But unfortunately, many people still use Pearson's method even when there are better methods available. Okay, so that's really very important. Okay, so let's move on to our second example. This second example is two interval scale variables. In fact, maybe it's actually two ratio scale variables. The y-axis here is a ratio of two measurements of babies, and the x-scale, the x-axis, is their age. If I remember correctly, it's their age in days. So let's ignore the statistics on the right to start with and just look at the scatter plot on the left. So if you take a look at this scatter plot on the left, if I asked you the question, indeed I would ask you if you were all in the classroom together with me, do you think that there is a relationship between ratio and age? So I hope you would say yes, there clearly is some sort of relationship between ratio and age. The more tricky question is, though, is there a linear relationship between these two variables? Meaning, do these points lie in a straight line? Well, having looked at the plot, I'm sure your answer will be no. Clearly, you can't draw a straight line that goes through or close to most of the points on this plot. So what might be going on? Well, it could be that there is a curved relationship between ratio and age, or you might even think, well, maybe this is made up of two lines. Maybe if I look at ages up to, say, 10 days, there's one linear fit, and if I look from 10 upwards, there's another linear fit. Is that possible? Well, actually, we know that with growth, with biological growth, growth rates are not constant across age, which is just as well. If you had ever seen me, I'm about 2 meters tall. Clearly, if I was continuing to grow at the same rate as I did when I was young, I wouldn't be able to fit in the building. So clearly we know that human beings don't continue to grow at a constant rate. And we know that growth either decreases slowly or there are growths for one period and not for another. But we know that growth is clearly not constant across life. So, however, If we look at what's on the right hand side, we're going to come back to what's on the right hand side in more detail, but what it's telling us is that if we put this data set into a statistical package and ask it, is there any evidence of a linear relationship? The answer that comes back is there is a very strongly significant result suggesting that there is a linear relationship between ratio and age. Now, of course, that doesn't mean this is a good explanation. It means that there is a linear component to this relationship. And indeed, we can see it is true that as age increases, so does the ratio. So even though a linear relationship may not be a good explanation, it's clearly a much better explanation than just saying that the ratio is constant and doesn't change with age. So we need to be very careful. But as we've said, if we look at this graph, it's very clear there is a strong nonlinear pattern in this relationship between growth ratio and age. And we'll come back and look at this data set again later to see what better we can do. Indeed, we can do something very quickly for a start. If we are more knowledgeable about biological growth patterns, we know that growth patterns are often exponential. If we have an exponential growth pattern, that means that if we log transform both growth ratio and age, we should get something that's a linear relationship. So here we see the same data set, but we've taken a log transform of ratio and a log transformation of age and then plotted our data again. We can see now that it's much closer to a linear relationship. It's not perfect. We can see it still looks a little bit of curvature towards the top, and the bottom point looks a little bit off. But you can see this is much closer to a linear relationship now than the plot we had just before when we plotted ratio directly against age. So what this is telling us is that we often do have at least approximately linear relationships, but it may well be that that's only the case after some form of transformation. And later on, we're going to look at transformations more carefully in order to try and understand this. We're also going to look more carefully at the summaries of the fit, this R squared and R squared adjusted things in the statistical summary, the root mean square error. We're going to look at all of these, and we're going to look at the statistical tests that we're doing here of whether the slope is 0 or not, because of course a 0 slope would mean there is no linear relationship. But again, we can see this is very strongly significant. Okay, so before we look in more detail at linear relationships, we're going to take a step back and look at the use of correlation. Right, so we're going to look first at how we can summarize a linear relationship using correlation. So correlation measures association in terms of how strong the linear relationship is, where a correlation of +1 means a perfect positive linear relationship. A correlation of -1 means a perfect negative linear relationship. 0 would mean there is no linear relationship at all, although there may still be a nonlinear relationship. So clearly between 0 and +1 would mean a positive linear relationship that does not fit perfectly. Between -1 and 0 means a negative linear relationship that again does not fit a line perfectly. So if R is not plus or minus 1, that can be because either the relationship is not linear or that there are random errors in either x or y. So the definition of R is the covariance of x and y scaled by the square root of the product of the variances of x and y. So that's all rather complicated. We don't need to worry too much about that. In fact, we're just going to skip over that part. The key point is that correlation is the joint variability of x and y scaled by the variability of both x and y. So in other words, it doesn't matter what the units are for x or y, it will have no effect on the correlation. So we're not going to look at these formula in detail. We can calculate the correlation, which we call R, based on a sample. And it's not hard to show that if y is equal to x, that R will be equal to 1. If y is equal to minus x, then R is minus 1. Or more interestingly, the more general equation of a line, I hope you remember from high school, is y equals a plus bx. So then R will be either plus or minus 1 depending on whether the sign of b is positive or negative. So the obvious hypothesis test is to test whether the population correlation is 0, but the standard test of this requires us to assume that both x and y follow a normal distribution. So if x and y follow a normal distribution with 0 correlation, then R over the square root of 1 minus R squared over n minus 2 follows a student t distribution with n minus 2 degrees of freedom. So if we have a sample size of at least 30, the t distribution is pretty close to a standard normal distribution, and so we can do this test. Now, if x and y both follow a normal distribution, then it turns out that independence is identical to 0 correlation. But that's not always the case, because 0 correlation just means no linear relationship, whereas independence means no relationship at all, linear or nonlinear. Now, we often use R squared as a way of summarizing the proportion of variability of one variable explained by the other variable. So you'll notice I've put explained in quotes, in double quotes. Why do I put explained in double quotes? It's because it doesn't tell us that we have causation. So we're implicitly assuming that there is causation, but it could be x causing y, it could be y causing x, or we could have a common cause W that's causing both x and y. Now, there's a whole field of statistical methodology that looks at correlations for large sets of variables. It's usually called either factor analysis or principal component analysis, but the mainstream approach is to build models for our linear relationships. So we're going to start with the simple linear model, the simple bivariate linear model. So we're going to write that simple linear model as y equals a plus bx plus epsilon. So that funny twiddles thing there is lowercase epsilon, a Greek letter. And you'll see I've put capital A as the intercept, capital B is the slope, x is our independent variable, y is our dependent variable. And we're going to start by making two key assumptions about the epsilons. We're going to assume that those random errors from different observations are independent, and we're also going to assume that they have constant variance. So in other words, this is just like elementary algebra except for the random error term. So if it was a simple line without epsilon, we would know how to estimate a and b. We could use linear algebra. As long as we had at least 2 points on that line, we know from linear algebra how to find a and b. But we can't do that this time because we have the random error term. So how do we estimate capital A and capital B? Clearly we want, in some sense, the best fitting model. So it turns out that if we have this constant error variability that we just said we will assume, and independent errors, that is a very general approach called least squares. This minimizes the squared errors. In other words, we're going to find estimates for capital A and B, and to avoid confusion, we call the estimates little a and little b. So capital A and capital B are the true values, and then little a and little b are the estimates. So we're going to find little a and little b that minimize the squared error for y. In other words, we want, if we look at the squared deviations of each observed y point from its fitted y point, we add up all those squared deviations and we minimize that squared error. So this can also be written as the summation of Ri squared, where Ri is the residual for the ith data point, being the difference between the observed and the fitted y for that point. Okay? Hence the name least squares. So it's possible to prove that this is the best way to fit a linear model if the error variance is constant, and we can also estimate the error variance from our sample. S squared will be the estimate of the error variance. It's the sum of the squared residuals divided by n minus 2, where n is the sample size. Now you might say, why are we dividing by n minus 2 and not dividing by n? That we can think of because we have used up 2 of the observations in order to fit the line. So if you remember, in linear algebra we can always fit a line perfectly to any 2 points. So because we have 2 parameters, we need at least 2 points in order to estimate the line. But if we only had 2 observations, we cannot estimate the error variance because it will always fit perfectly to any 2 points. Now the formula for little a and b are a bit complicated. We don't really need to look at these. The calculations are going to be done for us by our statistical package or our calculator. So the formula for little b I've written down here just for reference. We don't really need to know. Once we know little b, finding little a is very simple. It's just the mean of y minus b times the mean of x, because the mean of y is just a plus b times the mean of x. So that's very nice and simple. Once we know little b, we can always find little a. As I've said, in practice, we do not do the calculations by hand. Even simple calculators can do the calculations for us, or we can use a spreadsheet like Excel. And indeed, as I mentioned, we said we could show these are optimal. If your calculus is good, we can easily show that little a and little b are the optimal values that minimize s squared. So we use calculus to differentiate the sum of the squared residuals, and we can show that a and b are the values that minimize s squared. Now, you might think if I know little a, little b, and s squared, I should be in good shape. That means I would know the best fitted line if I know little a and little b. S squared tells me how much variability there is left over, which I didn't explain with my line. That seems like it should be a good summary of what's going on. So indeed, that's what most statistics packages or calculations will give you. But I want to indicate to you that without doing any form of graphics, there is a problem that these 3 numbers may not be a good summary of what's going on. So we're going to look now at 3 examples, each of them with a sample size of 11. Okay, so let's look at the first 2 examples here. So I want you to ignore the statistical analysis underneath. I just want you to look at the 2 graphics to start with. So if we start with the one on the left, if we look at the one on the left, the red line is showing us the linear fit to our data. And you can see here we have what I think you will agree is a reasonable linear fit. It's not terrible. It's not very good. Now, indeed, if you were all here, I would ask you how good you think this is. How good you think this is often depends on your disciplinary background. If, for example, you're an engineer and you look at a plot like this, you think this is really quite poor. There's so much unexplained variability. There's still a lot of variability around the line. On the other hand, if you're a social scientist and this is data on humans, you're probably very excited. We've explained so much of the variability. Indeed, if we look at the R squared value below, the R-squared value is about 66–67%, meaning around 2/3 of the variability has gone away after we have fitted our line. So 2/3, of course, is a lot greater than 0, but it's also not close to 1, so there's still quite a lot of variability that's not explained. But if I ask you to look at this, does it look to you reasonable? So one of the questions is, what is the reference point? As I've just said, if we've explained 2/3 of variability, that implies that yes, this is obviously much better than just fitting the average value of y, but it's still not good. So in that sense, perhaps it's not too bad. So is there anything obviously strange about this fit? If we look at the residuals, so remember the residual is the difference between the fitted and the actual value for each data point. So you can see we have a negative residual, a positive, a negative, a negative, a positive, a negative, positive, negative, negative. So the residuals seem to sort of be fairly randomly spread around our fitted line. It doesn't seem to be any obvious pattern. So you remember I said the two key patterns were that the errors from different data points were independent, so there doesn't seem to be any dependence here. And I said that the variance is constant. So it does look like the variance is reasonably constant around that line. There's no obvious sense in which the variance is increasing or decreasing across our fit. So in other words, this seems, as written above here, a moderate linear relationship. Not great, not terrible. So let's have a look at the plot on the right. So if you look at the plot on the right, again, if I ask you, does it look like there is a linear relationship here? Your answer is what? It is or it isn't. Clearly, a linear relationship is not a good explanation of what's going on here. But if we look at the fitted line for the left-hand side and the right-hand side, they both are y equals 3 plus a half x. They both have r squared is 0.666. They both have root mean square error, which is actually s, is 1.237. In other words, both of these data sets, we get the same fitted line and we have the same variability left after we fit the line, and we have the same value of r squared. But if we look at the one on the right, clearly this is disturbing. It looks like there is something else happening here. If you look at it carefully, you should be able to see there is a quadratic pattern, a parabola. And indeed, if we try fitting a quadratic relationship here, mean that we add in x squared as well as x into our fitted relationship, we discover it's a perfect fit. In other words, there is no random error whatsoever in the data set on the right. Once we fit the correct model, we discover there is no random error left at all. Right? It's actually a purely mathematical problem. There is no statistics at play here. There is no random error whatsoever once we have found the correct model. So I said we had 3 examples. Let's look at the third one. So the third example shows a very different pattern. So again, if I asked you, if you were all in a classroom with me, I would ask you to tell me, do you think that a linear relationship is a good explanation for what we see here? And usually when I ask that question, there's at least one student who will say, yeah, we need to remove that outlier, right? Meaning that one data point which is clearly different to all the others, they want to remove that data point. And my usual joking response is to say, goodbye Nobel Prize. Why would I say that? The honest truth is the most likely explanation of what's happening here is that somebody made a mistake. They either made a mistake when they were running the experiment, or they made a mistake when they were writing down the data, recording the data, or somewhere in the transfer process something went wrong. Because clearly that one data point is inconsistent with the rest of the data points. If we remove that data point, all the remaining data points fit perfectly to a line. Again, there is no random error if we remove that one data point. So it's very tempting to just remove it. But the honest truth is, we don't know if that data point is a mistake or not. So we know if we look back at the history of science, many great discoveries initially appeared to be faulty. People could not explain something, and then somebody else came along and said, actually, there is a good explanation. So if our y variable here was yield or some outcome that we wanted to maximize, if somehow we managed to get an output that was much higher for one data point than all the others, clearly we'd want to understand why. Now it's true, the most likely answer is we didn't achieve a much higher output, we just made a mistake. But without going back and checking, we cannot be sure. The key point is that, again, if we put this data set into the statistical package, we get exactly the same fitted line as the two previous examples, y equals 3 plus a half x, with exactly the same r squared, 0.666, we get the exactly same value of s, 1.236. So in other words, purely getting a and b and s and r squared isn't going to help us. We got exactly the same answers for these three data sets, but when we looked at the plot, it's very clear that what's going on is very different. If we go back and look at the previous one, the first one, as we said, clearly it's just that there's a lot of random variability we haven't explained, right? There's nothing obviously better than the linear model, but it's not particularly great. The second one, where it was simply the wrong model, that if we fitted the correct model, there actually is no random variable at all. And this third one, where it's one particular data point that is inconsistent with our model. The rest of the data points all fit perfectly. So obviously we will need to look at how might we be able to detect the problems with these data sets. We'll need to look more carefully at diagnostics. But first of all, let's look more generally at the linear model first. So we first of all need to note that correlation was symmetrical, right? With correlation, if we reversed x and y, we get exactly the same value for correlation. But the linear model is not symmetrical. If you reverse the roles of x and y, you get a different model. This is because our model assumes that all the measurement error is in y and not in x. Now, what about that statistical test? We actually haven't yet got to the point where we can do the statistical test because there's something missing. We need to make one more assumption. In addition to the assumption of independent errors and constant variability, we also have to assume what the error distribution is. If we can assume that the error distribution follows a normal distribution, then we can do statistical inference for the slope. Indeed, if it followed some other distribution, we could still do it, but it would just be a bit more complicated. So if the errors follow a normal distribution, we can then test the key hypothesis. The key hypothesis is whether b is equal to 0, capital B, because that means that y does not depend on x, meaning y and x are independent. So that's the same test as testing r equals 0. So essentially we're asking what values of little b we might expect if there is really no linear relationship between x and y. So little b is our test statistic. The errors follow a normal distribution with constant variance. If they do, then we will reject capital B as 0 if the value we observe for little b is too far away from 0 to be likely under the null hypothesis of capital B equals 0. So this test, the test for b equals 0, is based on the fact that we can find the distribution of little b. So the difference between little b and capital B, after we scale it by something called SB, which is the standard error of b, it follows a student t distribution with n-2 degrees of freedom. So what is S little b? S little b is just S, the standard error, remember, scaled by something that looks like the variance of x. So this will give us the standard error of b. That tells us how to scale, because if SB is small, that means we can quite sensitively test whether little b is different from capital big B. If SB is large, then we would need a big deviation of little b from big B before we can detect it. So notice that SB will decrease if the variance of x increases. This means, of course, we can also find a confidence interval for capital B. That confidence interval will be little b, which is our best estimate, plus or minus S little b, which is the variability, times our t cutoff value. So the t alpha over 2 with n-2 degrees of freedom is the cutoff value of a t distribution with n-2 degrees of freedom. And indeed, if the sample size is large, this t distribution is very close to a standard normal distribution. Now we could also test whether a is 0, capital A is 0. That would mean we're testing if y is proportional to x. That's not very often meaningful, but it could be if we wanted to know whether there is direct proportionality between x and y. So, as I mentioned just now, from those three plots, diagnostics are very important. And the simplest and most important diagnostics for regression are the residuals. So, the idea is that by plotting the residuals, we can get some idea whether there is an error in our model or in our data set. So we're going to go back and look again at our examples to see what they show. So the plot on the left is showing you for that first data set we had, the one where I said it fit moderately well, where here, after removing the linear part, you can see that we have a fairly random pattern around the 0 line. So remember, on average, the residuals are 0. This is showing you that they're varying between roughly plus and minus 2. And you can see there doesn't appear to be any obvious pattern in the residuals, and it looks like the spread is approximately constant. And I said that that was our other key assumption. On the other hand, if we look at the right-hand side, you can see that the second example, after we remove the linear part, we now have the perfect parabola. So it's so obvious that there's a quadratic pattern here. We've got that the residuals go from large negative up to large positive and back down to large negative in this perfect parabola pattern. So it's absolutely clear that we're missing x squared term out of our model. Rather than the third example, I've now gone back to the example we started out with about the growth of the babies. So this is the plot of the ratio against the predicted values for the growth example before doing the log transform. So here we can see very clearly a strong nonlinear pattern. So you can see that the first set of residuals are all negative, then they jump up to positive, and then they gradually come back down to negative again. But this is not like the simple quadratic pattern we looked at in this last plot. It's clearly something very asymmetrical, so that does suggest there is a need either to transform the data set or in some other way reconsider our model. So clearly our model is not good because we're not left with residuals which look in any way to be random around zero or to have a constant variance. There's clearly some strange pattern here which needs to be removed by finding a better model before we go any further. So let's come back to R squared. I said that R squared can be looked at as a way of telling us how good the linear fit is. So we can rewrite R squared as 1 minus the sum of the squared residuals over the sum of the squared deviations of the y values from the average value of y. In other words, this is telling us how much better is it than just using the average value of y. If R squared is equal to 0, that means that the sum of the squared residuals is equal to the sum of the squared deviations around the mean of y. In other words, the linear model is no better than a straight horizontal line through the mean of y. On the other hand, a perfect fit means the sum of the squared residuals must be 0. So that's why R squared is often interpreted loosely as the proportion of variability explained by x. As I mentioned before, I put this in double quotes to remind us this is implicitly assuming that x is causing y, which may not be true. It could be y causing x, or it could be the common cause w causing both x and y. So what about prediction? How can we predict y for a value of x? Well, it turns out we can just substitute into our equation using our estimates little a and little b. So the predicted value of y will just be little a plus little b times our x predictor value. And we can also estimate the prediction variability given the distribution of y predicted. So this is that the deviation of the predicted value from the true value of y follows a t-distribution after we scale by s-pred. So s-pred is s-scale multiplied by something a little bit more complicated. You'll see there are two parts to this. There's a 1 over n term, so that's the part that decreases as the sample size goes up. And there's another part which is the deviation, the squared deviation of our predicted x from the mean of x scaled by the sum of the squared deviations of x from the mean of x. So meaning if our x predictor is close to the mean, that second term disappears. If our x predictor is very different from the mean of x, we get a much bigger term in here, increasing our prediction error. So our prediction error is smallest for the mean of x and increases as the prediction x goes further away from the mean of x. But this is trying to predict the true value of y on average. If we want to predict y for a new individual, then we have to change s-pred to s-pred I. This, you will see, we now have an extra term inside the square root. We have an extra 1 in there because it doesn't matter how big the sample size is, we've always got the new variability of that new individual. Right? So even if n is very large, s-pred I can never be less than s. Right? Because we've got that variability from our new individual. So we can find confidence intervals both for s-pred and for s-pred I. I'm not going to show you the example here. There's one other very important point though we need to note here before we move on. This prediction assumes that our linear model is correct for that value of x. This may be a safe assumption if x is within the range of data we already observed. But what if x is either much greater or smaller than our data set? In that case, we have no real support from the data for believing that we can extrapolate like this. Right? So we need to be very careful that we should not be trying to make predictions outside the range of our data. If we do that, we need to be very cautious and warn that there is a risk here that we're assuming the model is still correct for values of x where we haven't actually observed any data. The other point is, as I highlighted up above, that a wider range of x values is generally a good idea because it means that SB will be smaller and SPRED will be smaller if we have that the range of x values is bigger. So we generally want a wider range of values of x if we want to have a good set of estimates for our linear model. Okay, so that's where we're going to take a break, and next time we're going to come back and look at multiple regression.